most of you have already, except a couple of people. But since we are not talking about that yet, I will set up the classical mechanics part a little bit later. Okay, David and Ryan, I guess. So I'll do that a little bit later. So what we're going to start off with is chapter 3 in the book, the mathematical methods, topics in contemporary mathematical physics, and the topic is symmetry and conservation. So we're going to start off, which is basically leading to group theory in physics. Start off talking about symmetry and conservation. Basically, the idea is that symmetries of physical systems will necessarily involve conserved quantities. And symmetry is best described using the mathematical language of group theory, and that's why since conservation laws are so important in physics, then it follows that group theory will be very important as a mathematical tool for physics. Okay? So to understand kind of more in detail how this happens, we're going to start off with a couple of examples. In other words, start off with the couple of conservation laws that we are mostly familiar with already. And now you think about what kind of conservation laws that you've learned, and probably most of you would agree that you all are or should be very familiar with. For example, conservation of linear momentum in classical mechanics, which says that when there are no external forces acting, then the linear momentum of a system of many particles is conserved. And also, there's what else? What other conservation principles are there? Perhaps the principle of conservation of energy, if there are no dissipation forces, and so on and so forth. And finally, conservation of angular momentum, okay, when there is what's called rotational symmetry in a system. So these are very basic symmetries. These are called space-time symmetries because the kind of symmetries that we are talking about involve symmetries when one does certain transformations in space, or more generally space-time. On a more general level, there are more abstract symmetries, such as the kind of internal symmetries that we talked about last time, conservation of isotopic spin and conservation of parity and conservation of other things and so on and so forth. But let us start off with the simpler things first. So let's talk about conservation of momentum first. Okay, this is a classical mechanics law. So we're going to start off with formulating a principle in classical mechanics which will allow us to see how symmetry comes into play and how conservation follows from that symmetry. Okay. Now, some of you have already taken my classical mechanics courses. Some of you have not, but in either case, it's okay. We're going to start off with what's called a Lagrangian approach to classical mechanics. Okay. What is meant by this? So, in classical mechanics, to keep things simple, let's say we are dealing with a problem of just one classical particle moving around in space, okay, and in time also. So we can visualize, for example, that there's a particle which follows a certain trajectory in time. And let's say as time increases, the particle goes in this way. And let's say the single particle is moving in three-dimensional space, okay? So a particular position of the particle will have associated with it so-called precision vector, all right? And now how do we specify this vector? We specify it by giving its three components, right? If we are dealing with a particle moving in three-dimensional space, then we have three components, x1, x2, x3. Now, in order to specify the path itself, you see, the components would then have to be given as functions of the time. So x1, x2, x3, all three functions as functions of time. So the idea is if you know these three functions, then from within a certain time interval, let's say, then you will have specified a complete classical trajectory between those two times. So let's say that the particle starts at a certain time t1 at this point in here, and ends up at this other particle at a later time t2, let's say, okay? And so I'm going to have, in order to specify this path in here, I'm going to have to specify these three functions, all defined within this time interval, t1 and t2, okay? Like so. Now, normally, you think of these three functions as being derivable from Newton's laws of motion, right? Given the forces, then you know how to use Newton's second law. M times x dot dot is equal to the force, and then you solve for x itself, and then that would be the answer. The answer would be given in terms of the three functions. But the Lagrangian approach is a different formulation of the laws of classical mechanics, which would eventually yield Newton's laws also, but which, as we're going to see, would make the applications a little bit more general, and it would open up avenues to other areas of physics also, as we described last time. Okay? But let's first see how the Lagrangian approach is being set up in classical mechanics. You first derive a quantity called the Lagrangian, okay, L, which in classical mechanics is defined as the difference between the kinetic energy and the potential energy. Those of you who have taken the advanced classical mechanics courses will perhaps remember that. So if we are talking about a single particle, the kinetic energy is 1/2 times the mass times the velocity squared, which is like, and I can write it like this, okay? But actually, you see, this square is actually the dot product of R dot with itself. So it's basically like dx1 dt times dx1 dt plus dx2 dt times dx2 dt plus dx3 dt times dx3 dt. Okay? So this is like a v squared, 1/2 v squared, okay? V squared is v dot v. V itself is dxi dt, so v dot v is just like this, according to the normal scalar product. Minus the potential energy. And the potential energy, in the case of conservative forces, is just a function of the various coordinates. Okay, it's not a function of time explicitly. Now I'm going to immediately write this a little bit better. I'm going to write this using the Einstein summation convention. I'm going to write this as dxi dt, dx sub I dt. Okay? Well, I is understood to be summed over, one up, one down, summed over from 1 to 3, 1 to 2 to 3. We call that our tensorial summation convention. Now, minus v, which is a function of all the xi's, so I'm just going to write it like this. Now, perhaps there's a question about the relative, positions of these indices in here. I've written this as 1 up, 1 down, but here we're talking about Euclidean vectors. So therefore, you raise and lower indices using the delta function, okay? And so once you have defined these upper index quantities as the contravariant vector, x1, x2, upper x3, then you can define the lower indices ones. Using the delta function as the metric, which is the one that is applicable to Euclidean geometry, then this is how it goes, okay? In more general cases, the metric would be something appropriate to the geometry under consideration. For example, you may be in space-time, you may be talking about the Minkowski metric, and then in more general curved space-time is the G mu nu, okay, as we have been talking about in mechanics. But in Euclidean space, for three-dimensional vectors, the metric is just the Kronecker delta, okay? And so, as always, the j is summed over, but when you sum over the j, there's only one value that counts, the one which is equal to I. So basically, subscript I is exactly equal to x subscript I is exactly equal to x superscript I in the context of Euclidean geometry, okay? So that's why it doesn't really matter here whether I write this as up or down, since the two are equal to each other. But when I write, so I want to write this as one up, one down, because I want to take advantage of the Einstein summation way of writing things. So I understand that when I see a pair of indices repeated, one up, one down, I understand that this is to be summed over. Okay? So that's kind of all detail to be gotten out of the way at the beginning. And so this quantity is called a Lagrangian function. Lagrangian function is a function of not only the coordinates themselves, but the time derivatives of the coordinates. Okay? And this is significant. It's a function not only of the coordinates themselves, but a function of the time derivatives of the coordinates. Out of this, we construct a quantity called a classical action. Out of the Lagrangian, we consider a quantity called a classical action, and this is usually denoted by a symbol S. Now, let me write this funny notation first, and then I'll explain what I mean by this. It means that the classical action to be constructed is actually a function of these other functions, okay? It's not a function of several variables, but a function of functions, okay? Because each of the xi is a function of the time t, okay? And then s is a function of these functions. A function of a function is sometimes called a functional, F-U-N-C-T-I-O-N-A-L. That's why this kind of analysis is sometimes called functional analysis. Okay? S is a functional of the classical paths in the following way. That means given a particular classical path, I will then be able to calculate a number called the classical action, which is calculated in this way. I sum over from the specified beginning time, t1, and the end time, t2, which are considered to be fixed times. And then I do the time integral of the Lagrangian. I do a time integral of the Lagrangian, which means I do the time integral of this business here, the difference between the potential energy, kinetic energy, and the potential energy. Okay? Now, let's make sure we understand what, even though we don't need to do this integral explicitly, let's try to make sure that we understand what this integral means. You see, imagine that you are given a particular trajectory. That means you are given a particular set of three functions, okay? x1, x2, x3, which all depend on time. So in the integrand in here, these guys are all time dependent, right? Are all functions of time. If the xi's themselves are functions of time, then the time derivatives are also functions of time. So this guy is a function of time, no doubt, okay? Now, if the xi is a function of time and v is a function of xi, then sort of through this chain relationship, the v itself can be considered as a function of time also. So the whole integrand is a function of time, then you can do a time integral from between two fixed values of time. In other words, after the integral is done, what you are left with is just a number, okay? Because you have integrated over time already, okay? So the functional can be considered as a mapping from the space of functions to the real line, okay? Given a particular set of functions, then through this procedure in here, you get a real number, okay? Such a thing is called a functional, as I said. It's a mapping from the set of functions to the real line. The real line meaning a set of real numbers. Okay, is that understood? So the classical action is a particular way where you can calculate a number from a given trajectory in here. Okay. Now what do we do with this functional? What we do is the following. So we can imagine a situation where you have many given trajectories. I have only drawn 3 of them between 2 fixed times t1 and t2. These paths can be considered as paths in 3-dimensional space. So the condition is that all these different trajectories are to start off from the same point and end at the same point. Okay? Now, given any trajectory, given any path, I can calculate the number, right? So if I take the top path, I come up with a number. I take the middle path, I come up with another number. I take the bottom path, I come up with yet another number in general. Here's a mathematical question. Which of the paths is going to give me locally either a maximum number or a minimum number?
Shortest.
The shortest? The shortest path gives the length, but this is not the length. But it's a good start. Okay.
What was the question?
Huh?
What was the question?
It's a variational calculus problem where you are required to find the particular path which gives either a minimum value or a maximum value for that functional. Okay?
Wherever the derivative is 0?
Yes, more or less. What is the derivative that we are talking about? Now, you must be thinking of ordinary calculus where, let's say this is a function, f of x, okay? There are many minima and many maxima, okay? Here's a local maximum, for example. Here's a local minimum, for example. Here's another local maximum. Here's another local minimum, for example, okay? Now here the mathematical question is quite a bit simpler. You're supposed to find all these values, x1, x2, x3, x4, and so on and so forth. You're supposed to find all these values which would actually give you either the maximum, local maximum, okay? Not a global maximum, local, okay? Which would either give you a local maximum or local minimum. Now, how do you do that in calculus?
You set the derivative equal
You
to
set the
0.
first derivative is equal to 0 and then solve that equation, okay? And out pops the various solutions. Those will be guaranteed to be the so-called extremal values, right? Extremal meaning either maximal or minimal, okay? Now here the mathematical problem is a little bit different. I'm not supposed to be solving for a bunch of values. I'm supposed to be finding some particular paths which would give me either a maximum value or a minimum value for this classical action. You understand what we're talking about? You understand the difference? In other words, I have to set some kind of derivative equal to 0, some kind of first derivative equal to 0. But this guy is not really a function of a bunch of numbers, right? But a function of the paths. So I have to define for you what is called a functional derivative and set that functional derivative is equal to 0 and then proceed to try to find out what the consequences of that condition is. Okay? So first of all, let me define for you the notion of a functional derivative as opposed to an ordinary derivative. This is a function of functions, so that's why I need to define a functional derivative, okay? Now, what do I want to do? The question I want to answer is the following. You see, you consider what happens to this classical action when you change the path slightly. Just like here, you consider what's going to happen to the function when you change the position of the independent variable slightly. That's what you do essentially when you try to calculate the first derivative, right? So instead of varying from one particular value of x to a neighboring one, you vary from one particular path to a neighboring one. Okay? So for example, if I start off with a certain path, which I'm going to call xi of t, okay? And using this particular path, I'm going to end up with some value, which calculated according to this way, which is the classical action corresponding to that particular path. Okay? Supposing I try to vary this path slightly, retaining the condition that the new varied path will also begin and end at the same point. So let me see if it makes sense to you. If I draw a new path to be something that's slightly different from the beginning path, maybe something like that. Okay? A new varied path, okay? Where at each point it differs from the original path, but slightly, just slightly. Okay? And I am going to write the new path as xit plus a small thing. Delta, I should write delta xi, not delta I. Delta xi is the slight change in xi, okay? Consider this to be a new function, which always assumes small values, okay? So delta x is just a slight change from x, okay? So at a particular point in time, let's say this time, for example, the original value of the x is here, the new value of the x is here, so delta x is just this little bit in here, like that, and so on and so forth. It can be positive, it can be negative, okay? But it's always considered to be a small form, okay? So I do a path variation, right? Which I'm going to denote by writing this. From the original xi, which is the old path, I go to a slightly varied new path, which is going to be xi plus delta of xi. Is that okay? And I now try to calculate, and retaining the condition that the new path begins and ends at the same point. So I would need to have delta xi at t1 would be equal to delta xi at t2 would both have to be equal to 0, right? Because the variation, if both paths start and end at the same point, then the variation is required to be 0 for both ends. Okay? Everywhere else it's not required to be 0. But at the beginning, at the end, it's required to be 0. Okay? I'm going to vary the path under this particular condition. And then let's see what happens to the change in the classical action as I go from the old path to the new path. Just as in the case of the function of one variable, I try to see what's going to happen to the function when I go from the original value to some slightly neighboring value. So this is the idea. Okay? So the quantity of importance is then, let me calculate S for the new path. Let me calculate S for the old path. And then I'm going to see what's the difference between them. Okay? Now let me write an expression for the classical action for the new path first. Okay? This is very straightforward. This is in the note, so you don't have to copy this down if you don't want to. It's in the notes, which I just sent to you. Okay? Let's do it very methodically. So this is equal to 1/2 m v dt. The first one is dx upper I, so it's x upper I plus delta x upper I times ddt x lower I plus delta x lower I. Remember that x upper I is exactly the same as x lower I for the Euclidean case, and delta x upper I is exactly the same as delta x lower I. But again, the I is supposed to be summed over between 1 and 3, let's say. Okay? Like this. Potential calculated with respect to the new path, xi plus delta xi, close bracket, like so. All right? We proceed. take the 1/2 outside. Oh no, not yet. Just do T1, T2, delta T. Um, 1/2 M times a bunch of things. Now this is the sum of two terms multiplied by sum of two terms, so you end up with 4 terms in here, like that. Okay, so let's write them down. First one, of course, is dx upper I dx small I dt. Okay, that's this times that. The second term is, now, the second term will produce something like xi ddt of delta xi, like that, right? And there's actually another term which is this multiplied by that, which is going to give us the same thing. So the two of those, okay? But here, when you differentiate this function, delta xi is something like this, right? The t in here is like that. Delta xi is just going to be, t1 starts off being 0. It always retains just some small values. T2 is equal to 0. So this is a delta xi. Okay, it's just a little bit different, right? Always 0 at the end. So this is T1, T2. This is delta xi, okay? I'm going to ask you to agree with me that ddt of delta xi is equal to delta of ddt of xi. Is that okay? Hopefully it's not too hard to say. In other words, these two operations are commutative, so to speak. Okay. So having done that, then I can write, now there are two of these terms in here. So it's d xi dt dt of delta xi, like that. All right, that takes care of this times that plus this times that, both of which yield the same thing, and so therefore we have the 2. Okay? Plus finally we have this times that. Okay? And I'm going to write this as ddt of delta x super I ddt of delta x lower I. At which point I can close off this bracket. So it's 1/2 m multiplied by all that. M is of course supposed to be a constant, that being just constant mass of the particle, minus V. Now here, when delta xi is small, I can do a Taylor expansion, okay? So I can write this as V calculated at xi plus delta xi times partial V partial xi. Is that okay? Like that. That's just an ordinary Taylor's expansion, retaining only terms proportional to the first derivative. It's a partial derivative because there are 3 x's in here. Okay. So and again, the i's are summed over, and sometimes, as I mentioned in 321, the tensor notation to use is this, right? That makes it a tensor, conform with the tensor notation. So there's 1 over I, 1 over I, which is something. Okay, everything clear to now? Okay. Now I play a little game in the next step. Write this as T1, T2, dt. First of all, let me take this first term, 1/2 m. Well, actually, let me factor out, still factor out this 1/2 m in here. I have x I t. So far, nothing is different. X I t. Now, let me write down this next step first and show that, we can establish this equality in here. Product in here. Minus And then
Just to start with,
I can close off this bracket here at this point. That corresponds to this one in here, and minus v x I minus delta xi. And I'm going to use this notation, e I v. And then I close off the curly brackets. Now, do you see how this is equal to this?
Yeah. You don't understand where you got the minus sign from.
Which minus sign?
The minus sign from right next to the two,
Yeah.
the two, not that one, that.
Yeah?
Yeah.
Well, this is what I'm trying to ask you to figure out. Okay? Or at least ask you to try to see whether you agree with that or not. Okay, let's work this out, all right? Forget about a factor of, well, look, let's start from here. Let's start from here, okay? Let's start from here. Here. If I write down here, can you see? This is blocking it. You have to write it out there.
Let's double check the schedule.
Okay, so let's see what comes of this, okay? 2 times, now here's the derivative of the product, right? So I use the product rule, right? So 2 times delta xi, then differentiate the second factor, which then becomes second derivative of dxi dt. Okay, and plus 2 times derivative of delta xi times the second factor, which is written the way it was. Right? Minus minus 2 times delta xi second time derivative. Like that. Okay. Here's the thing. Now, you see here, 2 of the terms cancel out, right? Clearly, right? The first and the third cancel out. Okay? Because of the minus sign. That's why the minus sign. Okay? It's built to look like that. Leaving this term in here, which is precisely which term? Which is precisely this guy in here. Okay? But wait a minute, we have this other one also. Okay, which I haven't written down. But you see, I don't want to have to write this down because this is second order in delta x. We're only writing things down to first order in delta x, as we do everywhere. You see, in this Taylor's expansion in here, I only keep things up to first order in delta x, as we do everywhere. So you have to be consistent in these, keeping things to the same order. And to things in the first order of delta x, which is all we are interested in. Because after all, you are varying it just tiny little bit, okay? So delta x already is very small, so delta x squared is even smaller, okay? Let's say, okay? So delta x squared can be taken to be 0, okay? So we don't have to include this, okay? It kind of like goes away. Put a curly because this is not a strict cancellation, but we are ignoring that on the basis of the fact that we are only keeping things to the first order. Now is that okay? All right. Now there's a reason why we want to do things like that. And it will become immediately clear. It produces what we call a surface term. Let me explain to you. This one is called a surface term. Which is going to give me 0 on integration. Do you see why? Do you see why? If you try to integrate something, right? What we are trying to do is this integral here. If you just take this term in here, well, the m is constant, 2 cancels out, blah, blah. What we're going to do, we're trying to do is essentially this integral here dt. The integrand looks like ddt of something, of some function, okay? Which is delta xi dxi dt. Now, can you tell me what that integral is? Let's write down a formal answer first. You're integrating the derivative of something. That's just that thing, evaluated at the two ends, okay? So it's like delta xi dxi dt evaluated at t2 minus delta xi dxi dt evaluated at t1. But wait, I have chosen the small variation to be such that its variation at the endpoints are 0. And so therefore that term drops out. That's why it's called a surface term. Surface in the sense that if I'm just looking at this in terms of, the function of one single variable, these 2 points are the two ends of the interval, which is like the boundary of a particular interval. Okay? So the boundary is kind of like a surface. Okay? When you do things in a higher order dimension than 3 dimensions, that becomes in quantum field theory later on, then it becomes a surface integral. You play much the same game when you try to formulate things in quantum field theory. Okay? So then the main reason why we want to write things in this way is that we can kill this surface term in here. Okay? All right? You kill that surface term, so what's left? This itself is not equal to 0. It is equal to 0 when you know the integration, right? But since we have to do the integration, we just take away the surface term, like so, okay? So this becomes a minus in here, right? Minus in here, like so, okay? And so, is everybody okay with that up to now? Fairly straightforward, okay? Go home and make sure you understand every single step. You're a little bit lost at this point. So what we are interested in finding is now the change in the classical action. When I go from the initial path to the new varied path, and that is written as delta S, by definition S at the new path, minus S at the old path. Okay? And as we have just seen, after the killing of the surface term, this is equal to dt. Now I just factor out the terms now that are, first I factor out the terms that are proportional to delta xi, right? Well, actually, wait. I have to subtract from this. Well, let me write this first. Okay, let me write this first in order not to confuse you. Let me write down everything the way we see it over there first. Okay, 1/2 m dxi t dxi dt. The surface term is gone, and then we have plus plus 2 times this guy, right? I'm sorry, there's a, wait a second, was that a minus or a plus? I think that's
It's a minus.
It's a minus.
It was a minus, right? Yeah, it was a minus. Yeah, that's important, I think. It was a minus 2 times delta xi. The second xi dt squared minus b xi, b evaluated xi, minus delta xi, partial derivatives. That's for this guy, right? The way we have written it down over there. Now to subtract from it the s for the original path. But the S for the original path, oh, where did I write the expression?
Professor,
Yeah.
you're distributing the 1/2, right? So does the 2 go away?
Yeah, I think I made a mistake. Oh, there somewhere. 1/2 m factors out 1/2 m. It only ends up here. And then the rest is okay. Is that right? Okay, thank you. All right. I have to subtract from it this guy. In other words, the integrand, it's the same integral, right? dt integral from t1 to t2, and I have to subtract from it. S is just 1/2 m dxi dt, dxi dt, that's the kinetic energy, minus the potential energy, which is d at the original xi. That's that. Okay? That's the original action, right? The difference between the kinetic and the potential. Now you see where the cancellations come from. That's exactly 1/2 m times this plus, and then now this minus. Okay? So those two are killed off. Kill off each other. Boom, boom. Where else is a cancellation?
The
The dx. So I have now minus b and now I have minus plus b. Okay? Boom, boom. Okay, so now I have the following. Let me put the next step over here. Okay. So this is integral t1, t2, dt. Now, all the terms are proportional to delta xi. Well, let me just write them separately first. Delta xi. There's a minus sign here. Now, I have to put the m somewhere. Let me put it inside of here. Okay. Factor out the xi in here, so that's the second time derivative. Okay, that goes for this term, right? And then the other term is just, what's left is just this term in here, right? Close this guy off minus delta xi. Let me write it a little bit differently. Instead of I, let me write j. It's just a dummy index. Anyway, so it doesn't really matter. There's a reason for doing that. You'll see a little bit later on. Is that okay? All right. Because if this is a dummy index, so I'm just going to change it to j. Okay. So far so good? One more step. Now going to factor out the delta xi. So I have first term minus m xi t squared minus let me write it like this. This is actually a j in here, but if I factor out delta xi, I have to write delta. This is simply the Kronecker delta. Okay, delta ij. Actually, when I factor out, let me write this as lower I, so that I can have the summation. Keep the summation convention. That's quite all right because lower I is the same as delta I. So write delta ij in here. Delta j. V. Let's see if you agree with me that this is okay. Now the first term is obviously okay, right? See that, right? I'm just factoring out this delta xi, the rest is just this. Now in here, when I sum over I, what's going to happen? Or when I sum over j, what's going to happen? When I sum over I, either way, it doesn't matter. When I sum over I here, there's an I to be summed over, there's j to be summed over also. But when I sum over I, the only term that contributes is j because of the Kronecker delta. And so it's as if I'm left with just a delta x to the j, and times a delta partial j. So it's okay. It's just a play of the summation convention. I hope by now you are familiar with that. It should not cause particular trouble. If you're still uncomfortable with that, make sure you go home and try to play around with that a little bit. Okay? There's a reason why I wanted to do that. Okay? Okay, at this point, I'm going to define what's called the functional derivative for you. Define that thing called a functional derivative. So I have this result that delta s is equal to that. Delta s is equal to that. Okay. Well, actually, let me take this expression. This is our result up to now. Delta s. Remember what delta s is? Delta s is the difference between the action at the new path and the action at the old path. That's defined as the change in the action. That's why we write it as delta s. And we have calculated it to be given by the right-hand side of that box equation. Okay, now let me define this what's called a functional derivative. Functional derivative is written using this symbol in here. This is kind of like a derivative sign. It's kind of like differentiating with respect to not the value xi itself, but the particular path xi itself. And it's defined in this manner that delta s is defined to be, since the whole thing is to be calculated in terms of an integral, right? The functional derivative ds dxi is defined by this expression here. Obviously, we want it to be proportional to the first variation of the path, okay? But then the classical action is supposed to be integrated over, so we retain this integral sign in here. It's a little bit different from how you define the ordinary derivative. Actually, quite a bit different. But in any case, you define it like this. You define it like this. Well, let's pause a moment and take a good look at that expression and try to see if you think it makes sense. Okay? All right. The first variation, this is called the first variation, the difference to first order in the variation between the values of the action, classical action, of course has to depend on the variation itself, and the coefficient of that under the integral sign is then defined to be the so-called functional derivative of this functional s. This thing is called functional derivative. Defined in this way, this thing is called a functional derivative. The way I write things, 3 lines means a definition. Okay? 2 lines means just an equality. Okay? So this is called a functional derivative. Of the functional s. It's a functional. That's why I use square brackets. Normally, if I use just the curly brackets, that would be an ordinary function. Okay? The functional is a mapping from a set of functions to some real number. An ordinary function is a mapping from real numbers to real numbers. Okay? So here's a difference. An ordinary function is a mapping from, if you talk about real value function of one real variable, is a mapping from a set of real numbers to a set of real numbers. A functional is a mapping from a set of functions to the set of real numbers. That means given a function, I can calculate a number. An ordinary function is given a value, I can calculate another value, which is f of x. Okay? That's a difference. And so the functional derivative has to be defined a little bit differently. Also, and I'm comparing these two equations, right? This one and this one. Then you can write down an expression for the functional derivative for our particular case. So that comparing these two equations, right? Then I have this result that the functional derivative of this functional s is then equal to just this guy in here, right? Is equal to minus, I can factor out a minus sign, right? Is that agreed? Just comparing those two expressions. Take a look at it carefully, okay? Is that okay? All right. Now here's the deal. In ordinary calculus, when you try to find minimum or maximum, you set the first derivative equal to 0. In functional calculus, when you try to find an extremum for a particular functional, you set the first functional derivative to be equal to 0. Now that's a theorem which needs to be proved, but I'm not going to do that, okay? I hope that you can just, based on sort of analogy between this and ordinary calculus, you can see what we are trying to do. In ordinary calculus, when you try to find an extremal value of a function, you set the first derivative of that function to be equal to 0, and then find out what the extremal values of the independent variable is or are. In functional calculus, you want to find, in order to find the extremal paths, so to speak, because the functional depends on the paths now, okay? You want to find the extremal paths by setting the first functional derivative to be equal to 0. Okay? All right. In other words, you try to set this guy to be equal to 0 to find the extremal paths. Okay? Well, what happens if you do that? Then the result is staring you in the face. If this is equal to 0, minus that is equal to 0, that means the thing inside the brackets is also equal to 0. Okay? If minus something is equal to 0, that thing is equal to 0. In other words, on setting functional derivative to be equal to 0, we have m d second xi d squared is equal to minus dv dxi. You know, you have the sum over j in here, right? You sum over j, the only term that contributes is when j is equal to I, so you write an I here instead and get rid of the delta function. Okay? Right? That's what we have. Now what is this? It's a differential equation, right? It is Newton's second law, right? Because for conservative forces, the negative gradient of the potential energy function is just a force. So the right-hand side is a force, the left-hand side, what is it? It's a mass times the acceleration. So that reproduces Newton's second law. So in this way, we see that at least in this particular case, where the Lagrangian is said to be equal to the difference between the kinetic and potential energies, the requirement that the functional S, the classical action, be extremal leads to this equation. And then you can find that particular path which satisfies this equation, which is then the classical trajectory that one can calculate from Newton's laws of motion. Okay? So the Lagrangian formulation is exactly mathematically, well, not exactly mathematically equivalent, but the results of the Lagrangian formulation of classical mechanics yield exactly the same results as starting from Newton's laws of motion. Okay, and we have shown that explicitly. And for those of you who are taking the classical mechanics course, we're going to do that later on in class also. Right? So you have a little bit of advanced kind of preview, if you will. All right. But I hope that this goes down, okay? It's not too difficult, okay? Any questions? I want to stop at this point and see if you have any questions.
I'm kind of curious why taking the Lagrangian method, like what advantages do you have versus this?
Plenty. We're going to show that. I cannot, this question is a very good question, but it cannot be answered in one sentence.
Okay.
The short answer is there are many advantages. In two respects. Number one, in terms of solving problems, okay, because these formulating the things can be Maxwell's equations in motion, which are Maxwell's equations, can be equations in quantum field theory, describing various interactions and so on and so forth. In this simplest context, you end up having Newton's second laws of motion. So the whole idea of variational calculus is much broader than classical mechanics, right? Because in a way of speaking, it's a fundamental approach in all of physics. Because you can, if you know how to build the action, right? If you know how to build the action starts out with a Lagrangian, then you integrate the Lagrangian. In the case of classical mechanics, you integrate it over time. In the case of relativity, you integrate it over four-dimensional space-time, and so on and so forth. Okay? So you see in quantum field theories, the action is built up from integrating what is called a Lagrangian density over a certain volume in space-time. Similarly, you can define functional derivatives, set it equal to 0, and then the resulting conditions would then become the equations of motion for the particular theory, so to speak. Okay? Very, very general. This is the modus operandum of basically what physicists try to do. So the first thing to do is to build up the action, in other words, to build up the Lagrangian density. But hey, what kind of clues do we have for building up a Lagrangian density? Because you don't know what the real physics is, right? You don't know what the fundamental forces are. Supposing you're here just a bunch of physicists, rather ignorant physicists, not knowing what the fundamental laws of motion are. How do we derive the fundamental laws of motion? The guiding principle is to choose a Lagrangian which leads to the action functional satisfying certain symmetry properties, such as rotational symmetry, such as Lorentz symmetry, such as more general kinds of symmetry, and so on and so forth. So you choose your Lagrangian. You don't know what it is exactly, but right from the outset, I demand that this Lagrangian to have this symmetry, that symmetry, that symmetry. Okay? Hopefully, the thing is when you work with those particular, the Lagrangian derived from those particular symmetries, you end up with a set of equations which you can solve, whose results can then be compared with experiments. And then you say that if it works, then you say that, I've gotten the right laws of motion. Okay? But when you think about it, really, if you don't know the details of the forces, let's say if you don't know exactly what the gravitational force is in Newtonian mechanics, all you know is that it is rotationally symmetric. Okay? You don't know that it's one over r squared law. All you know is that it's rotationally symmetric. But that's basically the situation, right? You don't know exactly what the force is like, but you require it to satisfy certain fundamental symmetries. Okay? A particular kind of symmetry is described by a particular group. That's why we refer to physics theories as kind of categorized by certain groups. This is a U1 theory, this is an SU2 theory, this is an SU3 theory, and so on and so forth. This is an SO4 theory, and so on and so forth. Okay? So that's how symmetry, which is a fundamental idea in physics, is so central and prominent in theoretical physics, especially the part of theoretical physics which deals with the fundamental laws of nature. Okay? All right, let's see. I wish I could sit down here all the time, but I will stand up again. But if you think about it, it's quite amazing, because when did Lagrange start? In the 1700s. He worked in the 1700s. He could not have foreseen the kinds of developments that were made later on in the 20th century, where we know how to deal with quantum field theory and so on and so forth. Does that answer your question somewhat?
Yeah.
Okay, there are plenty of advantages. And it's a fair question, it's a very good question, because you might think, since these two things lead to the same, why do we bother to formulate things in this funny manner and so on and so forth? Okay. All right, let's take a 5-minute break, okay? Before assume that we do have rotational symmetry, talking about symmetries now, okay? What do we mean by assuming rotational symmetry? Assuming rotational symmetry is rather like, we don't know exactly what the function potential energy is like as a function of all the different axes. All we require is that when we do a rotation, okay, of all the axes, the v doesn't change, okay? So in that case, then we have a rotationally symmetric Lagrangian. Now let's see what are the consequences of rotational symmetry. And I'm going to try to show you that the consequence is exactly nothing more and nothing less than the principle of conservation of the angular momentum by simply requiring rotational symmetry in a particular field, okay? In a particular class of mechanics. Now, in this step, we're going to see a little bit more of group theory coming into play, okay? So that's how I try to introduce group theory to you through specific examples, rather than trying to define the mathematical concept of a group as a mathematician would do and start from there, which is rather more abstract, which is much more useful in mathematics courses, but perhaps not in physics courses, okay? So, rotational symmetry. So let's start off with some general function like that, not necessarily rotational symmetric. Rotational symmetric means that, let's see, the three xi's kind of define a vector for you, right? When you give the three components, let's say in three-dimensional space, it defines a particular vector for you. This vector is a certain length. The length is given by xi, xi. Okay? Recall that it's just x dotted with itself. I summed over is x1 plus x2, x2 plus x3, x3, x1 squared plus x2 squared plus x2 squared. At this point, the potential would have a certain function. At another point, the potential would have a different value and so on and so forth. If this is rotationally symmetric, it demands that no matter how I rotate this particular vector, okay, so that it always ends up on the face of the sphere, the value of the potential is the same thing. Then we say that the potential function is rotationally symmetric. In other words, when this is the case, then the v can only depend on the value of the length of the vector rather than the direction of the vector, right? So this is the condition for rotational invariance. More specifically, well, if you want to write this exactly as the length, then you can write it like that also, because the length is the square root of x dot x, okay? Okay? So it's rotational invariance. Now, under the rotation, V does not change. And you can similarly see that the kinetic energy does not change also if you rotate the x, right? The kinetic energy is dxi dt, so the kinetic energy doesn't change either, so that the Lagrangian, which is the difference between the kinetic energy and the rotational energy, is also rotationally invariant, okay? In other words, V squared, which is V dot V, which is the factor going into the kinetic energy, is simply, as we wrote it, dxi dt, sum over t, okay? So this is also rotational invariant. You don't even have to write it like that. V squared being the scalar product of a vector itself. By its nature, scalar quantity is always rotationally invariant, right? Okay? The scalar quantity doesn't depend on the direction, okay? So the entire Lagrangian is rotationally invariant. And under this condition, we're going to try to investigate how does S change, or what is the functional derivative under the condition of rotational invariance, and also under the condition that Newton's laws are correct, okay, which we have demonstrated before, okay? Under these two conditions, let's see what will happen. Now, let me digress and do a little bit of mathematics first. Supposing I have a transformation xi going into x prime I, okay, which is the rotation of a particular vector, simple rotation of a particular vector. How can I write xi prime in terms of xi? Okay, in other words, if I have x prime 1, x prime 2, x prime 3, well, x prime 1, x prime 2, x prime 3 are the coordinates of the rotated vector. How are these things going to be related to the coordinates of the vector before the rotation?
Is this the rotation?
Just a rotation matrix, right? That was just an SO3 matrix, okay? So this is given by something in SO3 multiplied by x1, x2, x3, which is a 3 by 3 matrix, right? Which is a special orthogonal matrix because any rotational matrix has to be a special orthogonal matrix, right? What's meant by orthogonal again?
R transpose is equal to R inverse.
Exactly. The matrix transpose is equal to the inverse of the matrix. Okay. What does S mean?
Special.
So,
Special?
Determinant
What does that
equals
mean?
one.
determinant equals 1.
Determinant equal to plus 1. Plus 1. Okay? So let's get that clear. All right? So in general, I'm going to write this as, let's call the transformation matrix Aij. Like that. Is that okay? Okay, this is just a matrix multiplication, right? The Aij are the matrix elements of a particular SO3 matrix. Okay? Now this is any, now the matrix A, of course, because it is orthogonal, has to satisfy this relationship, right? A times its transpose must be equal to identity matrix because the transpose has to be equal to the inverse of the matrix. So A times its inverse must be equal to identity matrix. Any rotational matrix must satisfy this condition. Okay. It also satisfies the condition that determinant of A is equal to plus 1. Okay. But let's just make use of this condition first. This is a little bit more general. If the determinant may not be equal to plus 1. You know, you can think of this relationship, the orthogonality relationship, only comes from the requirement that the length of the vector remains unchanged. Okay? The fact that it is an actual rotation involves the condition that the determinant is equal to plus 1. You can think of an inversion, which is not a rotation. And an inversion preserves the length. It is not a rotation because the determinant is equal to minus 1. You see, if it's a three-dimensional, then the inversion matrix must be minus 1, minus 1, minus 1 along the diagonal. And that determinant must be the product of minus 1 and minus 1 and minus 1, which is minus 1. So it's not special, but it's orthogonal. Okay? All right. Because minus 1 times minus 1 is equal to plus 1. Okay? Now, here comes the theme. A is in general any finite rotation. That means rotating by finite angles. Okay? The way to deal with finite rotations is to deal with infinitesimal rotations first, both mathematically and in physics also. In other words, to deal with a finite rotation, you imagine doing a little bit of rotation at a time. Okay? In order to go all at once from here to here, you go boop, 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 and so on. Do a little bit at a time. Okay? Doing a little bit at a time leads to what we call Lie algebra. I'll try to explain from Lie group to Lie algebra. I'll try to explain what that means in particular a little bit later on, when we have a little bit more mathematics under our belt. But let's just keep this in mind first. So instead of looking at finite rotations, I am going to look at infinitesimal rotations, rotation by small angles, okay? Now, you know, in general, when you do an arbitrary rotation, it involves giving 3 angles. A rotation in 3-dimensional space involves 3 angles. A planar rotation only involves 1 angle, right? But when you do a rotation in 3 dimensions, it involves 3 angles. There are many choices for such a set of 3 angles, one of which is called Euler angles. We're going to talk about that later on in our classical mechanics course when we study the motions of rigid bodies, in particular the rotations of rigid bodies, okay? But it's important to remember that that an arbitrary rotation involves specification of 3 angles, 3 independent numbers specifying a particular rotation. Okay. Yeah.
And that's specifically because it's in 3 dimensions, SO3 rotation.
Because it's a rotation in 3-dimensional space.
All right. If it was SO4 or whatever higher dimension, it would
Then
be
you
the
have
number of
more
variables in that
independent
dimension.
numbers. Okay. And so on and so forth. In 4-dimensional space, there'd be 6, for example.
Yeah.
Okay. I guess you know that already, right?
Well, from pictures.
Yeah, later on we'll see. Okay. Now, there's a geometrical way of seeing that a rotation, in general, a rotation involves 3 numbers. Rotation in 3-dimensional space. A rotation can always be thought of as a rotation about some direction, right? A rotation can always be thought of as a rotation about some particular direction. But in 3-dimensional space, how do you specify a direction? You specify a rotation by specifying some unit vector pointing along some direction, okay? And you can think of a rotation by a certain angle about this direction, right? So if I say I have a particular rotation that's rotation around this particular axis and rotating around by a certain angle, how many numbers do I need to specify that particular rotation? You first need to specify the direction first. How many numbers do you need for that to specify direction?
3.
Just the direction.
1.
Just the direction. Well, you said 1, I said not correct. You've said 3, I said not correct. And the only other answer is 2. That's one good way of doing mathematics, by elimination. Obviously cannot be 4, right? Why 2? How do you specify a particular direction in space? What 2 angles do you give?
Theta, phi.
Phi and theta, right? Right? I mean, those are not the only choices, but you need 2 independent numbers to give a particular direction. Okay? Okay, so that specifies the axis of rotation, but then you have to say how much angle are you rotating about that axis. That's the 3rd number. Okay. In any case, you need 3 independent numbers to specify rotation in 3-dimensional space. Important factor. Okay? I'm going to show you pretty easily why it is like that, algebraically also, by going to the requirement of continuity. The requirement of orthogonality in the SO matrices. Okay? And in particular, by looking at what are called infinitesimal rotations. Infinitesimal rotation means hardly rotating at all, okay? I rotate just a little bit. That means that infinitesimal rotation is almost the same as the identity matrix, right? The identity matrix is not rotating at all, right? You're not changing the components of vector if you multiply by the identity matrix, right? So the identity matrix is not rotating at all. If you rotate it a little bit, you add to that identity matrix by just a matrix whose components are all very small. Okay? And so for infinitesimal rotations, I'm going to write A as equal to the identity matrix plus a small matrix, which I call epsilon. Okay? And all these are to be thought of as 3 by 3 matrices in 3-dimensional rotations. Now I impose this condition, right? A times A transpose is equal to the identity matrix. So I have 1 plus epsilon times, the transpose is, how do I write the transpose? What is the transpose? The transpose of a sum is equal to the sum of the transposes. What is the transpose of the identity matrix? Itself. Right? Now I don't know what this guy is yet, so I'm just going to write E transpose is equal to what? By requirement of orthogonality? 1. Okay? So far so good? I'll actually do some algebra, right? 1 times 1, identity times identity is identity. E times 1 is what? E, or epsilon. 1 times epsilon transpose is epsilon transpose. And then finally I have what? Epsilon times epsilon transpose. I don't know what that is. Epsilon transpose is not equal to epsilon inverse, because epsilon itself is not a rotation matrix. It's only part of a rotation matrix, right? So I don't know what that is yet. But I take advantage of the fact that I'm only considering infinitesimal epsilons. And I'm going to write my equation as we always do, just keep the equations of first order in the small quantities. And so what do? Take out that last one. Up to first order in epsilon. So, if epsilon is small enough, then I have epsilon plus epsilon transpose is equal to what?
0.
0, the 0 matrix, where all the 9 matrix elements are 0. The entire 3 by 3 matrix is equal to 0. Okay? What that means is epsilon transpose must be equal to what? Minus epsilon. So let's write out, in a very clumsy way, all the elements. Epsilon 1, 1, epsilon 1, 2, epsilon 1, 3, epsilon 2, 1, epsilon 2, 2, epsilon 2, 3, epsilon 3, 1, epsilon 3, 2, epsilon 3, 3. That's epsilon, right? So what is epsilon transpose?
The opposite.
You turn this around 90 degrees, right?
Yeah.
Epsilon transpose. So epsilon transpose is equal to E11, E21, E31. You see what's happening in here? E12, E22, E2, and E13, E23, E33. Has to be equal to minus epsilon. If this is epsilon, minus epsilon is this. Minus E11, minus E12, minus E13, minus E21, minus E22, minus E23, minus E31, minus E32, minus E3. I'm only doing this now because I do want you to see exactly what's happening. From now on, I won't be writing out matrices because I get very tired and I will make mistakes if I write out larger and larger matrices. Okay, but I do want you to see exactly what's happening. This matrix is supposed to be equal to that matrix, right? When two matrices are equal, all the individual matrix elements in respective positions are supposed to be equal to each other. Right? So first I have these three guys. E11 is equal to minus E11, E12 is equal to minus E22, and E33 is equal to minus E33. That means what? Yes, anti-symmetric. So what must E11 and E22 and E33 be all equal to?
0, 0.
0, because a number that's equal to its own negative has to be 0, okay? Furthermore, if you look at the odd diagonal matrix elements now, E21 is equal to minus E12, E31 is equal to minus E13, and so on and so forth. In fact, you're right. The matrix has to be anti-symmetric. Anti-symmetric, okay? That means E must look like this. For all the diagonal elements are equal to 0. This is E12, E13, E23. But E21 is equal to minus E12, so these two are the negatives of each other. These two are the negatives of each other. These two are the negatives of each other. So how many independent numbers are there? 3. So to specify specify infinitesimal rotation in 3 dimensions, you need 3 independent numbers. You need 3 independent numbers. That's why, okay? And you can apply the same consideration and justify that the same is true for finite rotations also. Okay? Although I have kind of tried to make the argument in a geometrical fashion just now. Okay? You need 3 independent numbers. Usually bigger than these 3. You need 3 independent numbers to specify a rotation. The reason is because that came from the requirement of orthogonality, and rotation matrices must be orthogonal matrices. Okay? Actually, this specifies something other than rotations. Also may include inversions or inversions plus rotations. Also, but definitely for rotations, this has to be true. Yeah?
Are you adding the E transpose or the epsilon transpose and the epsilon to get?
No, I'm not.
Or you just
I'm applying
comparing?
this. E transpose must be equal to minus E.
Okay.
Okay? So this is E transpose. I'm requiring it to be equal to minus E. So now I compare element to element. This one is equal to this one is equal to this one is equal to this one. That's all. So I hope that you will agree. From now on, whenever you see a matrix like this, then you know without having to write out all the matrix elements, you know this is an antisymmetric matrix. Antisymmetric matrix. Okay? Now let me ask you, rather. Supposing I come up with an n by n matrix. And I tell you that matrix is anti-symmetric. Okay? How many independent numbers are there in an n by n anti-symmetric matrix? Now I know that all the diagonals must be equal to 0. Okay? Now these, because it's anti-symmetric, these must be the negatives of those. So the question is, how many numbers are here in an n by n matrix?
The n factorial.
Think about it a little bit first.
N squared minus
Rather than jumping to
It's
conclusions.
n plus 2.
N squared minus n plus 2.
Something like that. Yeah. But it's, I think it is. But you can see that very easily. Altogether, how many elements does an n by n matrix have? N squared. You take out the diagonals. How many diagonal elements are there? N. So it's n squared minus n. And then it's only 1/2 of those, right? So it's n squared minus n divided by 2. The independent elements in an n-symmetric matrix, n squared minus n divided by 2, which is n minus 1 divided by 2. So if n is equal to 3, this is 3 times 2 divided by 2 is equal to 3. If n is equal to 4, then this is equal to that, which is equal to 6, and so on and so forth. Okay? And you can figure out very easily for an arbitrary n by n matrix, what is the total number of, for an n by n anti-symmetric matrix, how many independent elements are there? It's n squared minus n divided by 2. Okay? Okay, so let's say we deal with this particular kind of infinitesimal matrix in here. Which is a condition that is necessarily satisfied by any rotation matrix. Rotational, infinitesimal rotation matrix. And infinitesimal rotation matrix is always written like that. Epsilon is small. Okay. And so now, let's figure out what the transformation looks like. Okay. If I let Aij be delta Ij plus epsilon Ij, right? The identity matrix is delta Ij, Kronecker delta, right? The epsilon Ij is whatever it is, okay? so x prime I must be equal to aij. Aij is delta ij plus epsilon ij xj. Okay. And that is, the first term, of course, is just, when you sum over the j, is just x pi, right? Right? Delta ij multiplied by xj summed over j is just equal to x pi, okay? Plus delta ij xj. Now, since this is supposed to be an infinitesimal rotation, so this term is supposed to be very small because it hardly rotates, so the components are almost the same as the original components. Okay, so I'm going to write this as delta xi, okay? Delta xi. So I simply call this delta xi, the change in xi. The change in xi imposed on top of the xi will give me the new xi, which is x prime I. Okay, easy enough, all right? And so, so then I know that delta xi must be equal to epsilon ij xj. So if I know what the epsilons are, and I know what the original components of the vector are, then I can figure out the change under rotation, under that particular infinitesimal rotation. And don't forget that this condition has to be satisfied, which means epsilon ij is equal to minus epsilon ji. That's a condition of anti-symmetry. Okay? So, you see, when we vary that action functional, we try to calculate its value when a particular xi is changed to xi plus delta xi. So we're going to play the same game, but the delta xi is given by this expression in here, under rotation. In other words, we're going to try to figure out what the change in the action functional is under an infinitesimal rotation of the xi. Okay? And referring to an earlier result, you're going to find this. And delta s. 3.6, I don't know if you have the notes in front of you. This is an equation which I wrote down earlier. This is the integral from delta 1 to 1 to 2, delta t, factorial to delta xi. There's this guy minus m. Well, this is our earlier result. Let me write it down. Now let me include this, let me include the surface term here. Let me explain to you in a little bit why we have now to include the surface term. Because we're dealing with a different kind of transformation. Before, multiplied by m, which is a constant. Before we were dealing with a particular kind of variation where the delta xi at both ends has to be equal to 0. Okay? But we are now dealing with a different kind of transformation where delta I is different, not necessarily equal to 0, both, because it's a rotation, it's a different kind of transformation, not necessarily equal to 0 at both ends, so therefore we have to keep that second term. Okay? You see the difference in here between what we're doing here and what we did earlier on. But having gone through what we did earlier on, we know that this is equal to 0. Because this is Newton's second law. Okay? In fact, that's equal to 0 is Newton's second law. So we end up with a situation where under rotations, the delta S is equal to both. Is equal to that. Okay? Under rotations. No, that's equal to that.
differential symmetry is on the rotation.
under rotations. The symmetry is then imposed by requiring that the integral is equal to 0. Okay? Functional, because that's a functional. Well, yeah, that equals 0. That's a symmetry. Symmetry means that my S does not change under rotations. If my S does not change under rotations, then delta S is required to be 0. Okay? That's when the rotational symmetry is imposed. That's the place where rotational symmetry is imposed. It's imposed by requiring that the functional does not change its value when all the x's undergo rotations. Okay? Well, this integral is easy to do because now if that is required to be equal to 0, then you don't have to write the m in it, and it's just a positive constant. Okay? And so this is a requirement now. But this integral is formally easily done because it's then just this quantity evaluated. The difference between the values of this quantity at the 2 times must be equal to 0. In other words, I'm going to write this as delta x phi, dx dt. This one evaluated at the 2 ends must be equal to 0. Now T1 and T2, we haven't specified those times, so those can be any 2 times whatsoever. So that ends up meaning what? That ends up meaning that quantity must be constant as time changes. So there's a conservation of something. Okay? That quantity must be constant as time changes. So that means this, that m times dxi dt times delta xi is constant in time. Okay? Okay, play a little game in here first. This is still understood in the sense of the Einstein summation. Okay, well, I is to be summed over.
Professor,
Yeah.
how did the del S become just the surface term only?
Because now I cannot just get rid of it before the imposition of the symmetry requirement. I have to retain it first. Okay.
I mean, at first there was
At first there was this other thing.
there's 2 integrals.
The 2 integrals. The first one is gone because the integrand is equal to 0. The integrand is just the integrand is just what? M is just m times the second derivative of x is equal to the force. That's always equal to 0. We've shown that already. Okay. We assume that Newton's laws are obeyed. Okay. So the first integral is gone. Okay. So that we are just left with what's called a surface term, but the surface term cannot be arbitrarily set equal to 0 until you impose the condition of rotational invariance. Is that okay? All right. Is that okay with everybody? Okay. If the first term were not equal to 0, we'd be in trouble. If the first term were not equal to 0, first integral were not equal to 0, Newton's laws would not be correct. And we'll have to redo all of physics. Okay? All right? Okay, let's continue. Okay, 5 minutes. I think. Okay. So let me write this as m dxi dt delta xi. So delta xi, let me write this as epsilon I j xj. Is that okay? That's delta xi, right? That's delta xi. I'm going to write this as, because I want to write this x up lower in terms of x upper. And so I'll write this as m xi T delta I J epsilon J K X K. Because delta I J, oops, let's see, delta I J X K, yeah, like that, okay. So then there are really three sums in here, I, J, and K. And I'm now going to define this as M epsilon jk. Now remember, these are the arbitrary constants specifying the rotation, okay? The rest of it, I'm just going to call it as a tensor, which is t, k, j, like that. Where now t, k, j is obviously defined as this multiplied by this multiplied by this, okay? So tkj is delta ij xk dxy t, and so I'm left with one of the subscript, which is k, one more subscript, which is j, the other one I sum over, so it doesn't appear.
Okay.
Okay. So I've defined a quantity, tkj, for you. And so let's actually try to write this out. Okay, after we've done the sum in here. And so after we have done the sum, this is then going to be equal to, you see, this is anti-symmetric, right? So at least these two indices have to be different, otherwise it would be 0, right? But then when you have jk and kj are related by a minus sign, okay? So you end up with only 3 independent terms because there are 3 independent numbers. Okay? So I can write this as m epsilon 1, 2 t1 true minus t2 1. When you sum over, I can have 1, 2, I can have 2, 1, but one is the negative of the other, and I combine them like this, okay? Plus m epsilon 1, 3, t1, 3 minus t3, 1, plus m epsilon 3, 2, t2, 3 minus t3, 2. That's what this guy is equal to. So now let's further define a quantity that I'm going to call this other tensor that I'm going to call Lij, and I define that to be the tensor minus m times t by j minus t ji. So obviously I want to do that because there's this combination in here, tij minus tji. So this would be L21, for example. This would be L31, this would be L32. Okay? So after I have done that, then I'm very close to the end. And now define Lij. Well, the thing is, we said that this would have to be a conserved quantity, right? This whole thing would have to be a conserved quantity, okay? Now, the thing is that these guys are arbitrary numbers because there are 3 independent numbers in that infinitesimal rotational matrix. And so Tij, let's see, now let's see, with the Tij, let's take a look at this guy. This guy looks like some component of x multiplied some component of the derivative of xi. And in fact, you can raise. Let me now just try to raise one of the indices. Okay, make it into a totally contravariant. So let's start with this guy. I'm going to define Tij to be delta ik tjk. Okay, so I have raised this index in here. Sum over k, so this becomes a j over k. This is how we usually raise and lower indices. Do you remember back from physics 131? And if we do that, then the Tij from that equation just becomes xj multiplied by dxi dt. So now Lij can be similarly, I can raise the index also, right? If I define Lij by upper ij by raising an index, I can now write Lij is equal to m times Tij minus Tji. Okay? Where Tji is given by that. And so, what I can conclude now is that the Lij's must be constant. What is the Lij's is because these epsilons are independent, right? And so it means these guys are independent, are conserved because the whole thing is conserved, right? The whole thing is conserved. Epsilons are independent, so each of these guys must be independent of time. So each of the Lij's must be independent of time. But if you use this expression for Tij, and really this is the end result in here, so I can have Lij is equal to, I can define this to be m xi dxj dt minus xj dxi dt. Take a good look at this. Can you tell what that is?
Is that a minus?
The conservation of the momentum.
This is a minus sign.
Conservation momentum.
That's conservation. That's angular momentum, not momentum. Angular momentum. Angular momentum. There are three independent angular components in here: L12, L23, and L1, L12, L13, and L23. Those are our usual Lx, Ly, Lz. Okay. Now, in classical mechanics, the angular momentum is defined in terms of a cross product, right? Okay. And when you have the first component of this, then this is the, it's the second component of this multiplied by the third component of this. When you do a cross product, what do? You have that kind of difference. Okay? Go home and check that. Make sure that you understand that this is the angular momentum. So all the Lij's are conserved. That means the angular momentum is conserved. All three components of the angular momentum are conserved. Okay, so that's how the conservation of angular momentum comes about. But when you try to trace it back to what we were doing, this arose from the fact that we imposed rotational invariance on the classical action. Okay, so conservation of angular momentum follows from rotational invariance. So this is one particular instance where a particular conservation law comes from a particular kind of symmetry. Rotational invariance is a symmetry, okay? So rotational symmetry leads to conservation of angular momentum. One of the first exercises, this was the first exercise asked to show that based on similar but in fact easier arguments, translational symmetry leads to conservation of linear momentum. You're supposed to show. Now finally, let me just, I mentioned this already, but here Lij, there are three independent components in here, right? L12, L13, and L23, right? Because L21 is the negative of L12, just based on the definition in here, okay? So when I and J both can involve all three numbers, then they're just three independent components. L11 is definitely equal to 0. You can see from this in here quite easily. L22 is equal to 0. L33 is equal to 0. So the only non-zero ones are the off diagonal, so to speak. You think of this as a matrix. This is a 3 by 3 matrix, right? But because of this negative sign in here, the matrix is anti-symmetric. Okay? So again, how many independent numbers does an anti-symmetric matrix have? 3. And so the matrix will look like this. The L matrix will look like this. 0, 0, 0, L1, 2, L1, 3, L2, 3. All this is just minus L1, 2, minus L1, 3, minus L2, 3. So independent numbers are these ones. Usually we follow this 1, 2, 3 permutational order. And we define L1, 2 to be equal to the first component, L1 through 3, the third component of the angular momentum. And this is a special situation where you have, you just have the right number of independent elements in a three-dimensional situation, so that you can associate it with the components of a vector. But this is not a real vector. This is one of those we call pseudo vectors. Why? Because the angular momentum is defined in terms of a cross product, and we talked about already in physics 321 that a cross product is not a real vector. It's a pseudo vector. A pseudo vector is really not a vector at all, but a rank 2 tensor, a matrix. Okay. So we associate L1, 2 equals 1, 2. This is L3. Then we associate L1, 3 with what? It goes in the opposite direction, which is minus L2. Okay. And then we associate L2, 3 with L1. So those three are the three independent components of the angular momentum. All those three are constant in time, so therefore this means that all the components of the angular momentum are constant in time. This means that angular momentum is conserved. Okay? You go 1, 2, 3. If you go in the opposite direction, it's a minus. Okay? So 1, 2 gives you a 3. 1, 2 gives you a 3. 1, 3 gives you a minus 2. And 2, 3 gives you 1. We encountered this already a few times back in physics 320 when we talk about cross products. All right, I think it's about time to